This is example 14 taken from Year 1 Pearson Mechanics, section 10.6 Pulleys. Two particles A and B of mass 0.4 kilograms and 0.8 kilograms respectively are connected by a light inextensible string. Particle A lies on a rough horizontal table 4.5 metres from a small smooth pulley which is fixed at the edge of the table. The string passes over the pulley and B hangs freely with the string taut 0.5 metres above horizontal ground. A frictional force of magnitude 0.08 g opposes the motion of particle A. The system is released from rest. And then it goes on to find and asks you to find different things in A, B and C. To start this question, we need to draw a diagram. Okay, so I have drawn out my diagram. I've put particle A, and starting here I'm told that at the beginning that A has a mass of 0.4 kilograms, so that means I can write 0.4 g acting down, and there's a normal reaction which I'm just going to call R at A because it's the normal reaction for A, and it's a light inextensible string, so this string is going to have tension in it. Remember, the pulley is smooth and it's not inextensible, so all those tensions are going to be constant throughout. It lies on a rough horizontal table of 4.5 metres from a smooth pulley. I'm not going to yet put that on, I might need to later. It says the string passes over the pulley. I do actually need, just thinking about it, to put in the mass of my particle B because I haven't put that in. Now, have I got any other forces here? The frictional force. So it's quite important we go through and we make sure we have included all the information. It does include that it's 0.5 metres above the horizontal ground. I could well come back and put that in as well, but I won't at the moment. So the frictional force, so if it's frictional force, it's going to act in that direction. And I'll explain why in a moment. I'm just going to actually go to the system is released from rest. Now, let's think about what would happen when this was released from rest. If you haven't watched example 13 video, it may be worth going back to look at that. But again here, which is the item with, so the particle with the most mass, is it A or is it B? It's B. So it's going to accelerate in that direction. So that's the direction it's accelerating. So if we go up here, what direction is it going to accelerate? It's going to accelerate in that direction. So it's going to release from rest and it's going to start moving. And that's why I know that my friction will act in this direction. So you do need to put on, to start with, the direction of the motion. Before you can put friction on, because remember, friction always opposes motion. So, having completed our diagram, the next thing I need to look at is A, which is the acceleration of the system. So when we're asked to do this, we do need to think about resolving, and we did this in example 13 previously, and we do each particle separately. So if I look at A to start with, I'm going to resolve parallel to the plane using F equals ma. And the reason I'm doing parallel to the plane is because that is the direction of the motion. The direction of the motion is parallel to the plane. If I resolved perpendicular to the plane, those forces are in equilibrium. So we've dealt with that before, because the upward forces, so the normal reaction is equal to the weight acting down. They are in equilibrium. The direction that it's moving in is parallel to the plane, so that is the direction that we are going to look at. So using F equals ma for A. So we're just doing this for A at the moment. We're not looking at anything else. So forces in the direction of motion. So look at A here, which is in the direction of motion, is T. And forces in the opposite direction, minus or subtract 0.08 g, equals my mass, which is 0.4, and my acceleration there. So that's one equation that I found. And I'm going to go on now, and I'm actually going to do the same, but I'm actually going to look now at particle B. But for particle B, the motion, if you think about it, is vertical. So here I'm going to resolve vertically for particle B using F equals ma. So again, forces in the direction of motion, so downwards is 0.8 g. Forces in the opposite direction is T, and that would equal my mass, which is 0.8, multiplied by my acceleration. So there is a second equation. So if you ever get stuck on one of these questions, can I just say, for pulleys, the best thing to do is to actually resolve using F equals ma for each particle separately, and then see where you can go. So now from here, where can I go? Well, I can find the acceleration because I've actually got two equations now here, which I can solve simultaneously. So if I add together the first equation and the second equation, my tensions will cancel, which couldn't be better, and I'm going to be left with minus 0.08 g, add 0.8 g equals 0. Actually, if I move across, I don't need to write it underneath there, equals 0.4a plus 0.8a. So then that would give me 0.72 g equals 1.2a, and therefore if I do some division, I'm going to end up with a equals 0.6 g, and I can write that as meters per second to the minus 2. So when I come back, that's what I may use, but for the point at the question that I'm at, I'm going to actually also write it to 3 significant figures, and I get 5.88 meters per second to the minus 2. And that's part A answered. So I've now calculated A, the acceleration of the system, and I'm now going on to part B, which is the time taken for B to reach the ground. And if we remember back to the question, it's really important at this stage. It's very easy to get stuck and forget things. And maybe this is where a highlighter pen would come in useful, because in the question it does say, if we go back, there's this piece of information here which says it's 0.5 metres above the horizontal ground. And therefore, I need to use that information because it's going to start moving and it's then going to move 0.5 metres and then it's going to reach the ground. So just moving up here slightly, what information do I have? Well, I know for part B that u is equal to 0 because I know it started from rest. I know from the information from my question, I know that it's going to move 0.5 metres before it reaches the floor. I've also worked out my acceleration. My acceleration was 0.6 g. I'm using the exact figure. Remember, I always go back and use the exact one, though I do realise 5.88 is exact, but sometimes that might have been rounded. And what I'm wanting to find is t. So here I'm going to use my Suvat equations and I'm going to use S equals ut plus half at squared, and u is 0, so I'm going to have 0.5 as S, and u is 0, so 0 times t, that's 0 plus half multiplied by 0.6 g, because that was my acceleration, times t squared. Therefore, I'm going to end up with t squared equals 1 divided by 0.6 g. If you're wondering where the ones come from, it's because of this half. When I multiply by 2 this side, I get 1 divided by 0.6 g, and therefore I can find that t is equal to... Okay, I'm moving on to the final part now, so let's go back and have a read of what that is. It's asking for the total distance travelled by A before it comes to rest. So if we look at our diagram for A, it's going to travel along until B hits the floor. Now at the point B hits the floor, it's travelled 0.5 metres because A and B are connected. So if A and B are connected, whatever distance B travels, A then travels as well. So up to the point where B hits the floor, they're travelling the same. They've both travelled 0.5 metres. After that point, things change though, because A now doesn't have tension in the rope. There is no tension, and we need to think about what does that mean, because if there's no tension, there's nothing pulling it along anymore, nothing pulling it in the direction of the pulley. So it's going to start decelerating because it's still got a frictional force acting against its movement. So now we've got a different acceleration. And there's lots of things I don't know and lots of things I might need to find out. So let's go over here and we're going to look at C. And first of all, what do I know? Well, I know that it travels 0.5 metres then B hits the floor. I don't know the speed though of A, and that actually would help me if I did know that speed. So I do know some information that would help me find what that speed is. So I know that for A, that my speed would be 0. I know then I've got the speed of A when B hits the floor. My acceleration, well, I know my acceleration. I worked that out previously, so let's go back and have a look. Where is my acceleration? There it is, 0.6 g. And how long does it take? Well, the time is the same as the time it takes to hit B, for B to hit the floor, because A and B are connected and all the forces acting on them are staying all the same, modelled by those two separate equations, until B hits the floor. So if we go, the time taken will be the same as here, which is 0.412393. So I'm going to write 0.4912,393. And I think if you look in the book looks at finding out the speed of B. Well, that's equally okay. The speed that B hits the floor at is actually the same speed that A is moving at, because they're moving at the same speed because of they're connected particles. So yes, you could look at finding the velocity of B as it hits the floor, and that's the same as the velocity of A when B hits the floor. So looking at this here, what would I use? Well, I'm going to use V equals U plus AT. So I'm just substituting in my values now. And this needs to be put in a calculator. So the value I ended up with here is, having typed it into my calculator, is 2.42487. And I'm going to leave it like that because actually I'm partway through a question. I'm only going to write 3 significant figures when I get to the end of the question. This isn't the end of the question. So that is the velocity of A once B has hit the floor. Okay, so what we're needing to find out is the total distance travelled. So I want to know how far A carries on moving. So I've got that the initial speed, if you think about it, the initial velocity when A is about to move off on its own when it's not interconnected. So let's see, what could I look at? So for the stage that I'm at now, I know that therefore when it starts moving off on its own, the initial speed now becomes the speed it was at when it was connected. I want to find out what S is, because that's quite important, because that's what the question is asking about. What else do I know? Well, I know what's going to happen is it's eventually going to come to rest because it's got this frictional force acting on it. So I do know that V equals 0. And I know it's decelerating. So I could find out what A is. And that's what I'm needing to do, which needs me to draw a new diagram of what's actually happening to A now. Well, A is still a block on a table. It still has this force in this direction, which is 0.08 g. However, it now doesn't have a force acting in the opposite direction. However, it is travelling still in that direction. So I'm going to use F equals ma for this for just A in the system at this point, because remember there is no tension again because the rope has gone slack. I need to keep emphasising that the rope's slack because B has hit the ground. So there's no tension now. So forces in the direction of motion, none. Forces in the opposite direction, there we go. And that equals my mass times my new acceleration, okay? Because the acceleration is now going to be deceleration. And if I type that into my calculator now, so my answer for my calculator is negative, because it's deceleration, 0.2 G. So I've now found a value which I can put into there. So I've got U, I've got V, I've got A now, and I want to find S. So if I go, so V squared equals U squared plus 2AS naught or 0 equals 2.42487 squared plus 2 multiplied by negative 0.2 G times S. So if I tidy that up, I can write naught equals 5.87999. I've got the rest of that in my calculator, so I am going to use that. Subtract 0.4 GS, and therefore 0.4 GS equals 5.87999, and as I said, that carries on in my calculator, and I can now work out my displacement. So my displacement comes out to be 1.49999. I think it's 4 nines, then an 8601. So I'm going to take my displacements as 1.5, and that's to 3 significant figures. Remember about rounding. Maybe I should put the 0 on the end. So my total displacement, because remember, this has been going on a while, so you're more likely to have forgotten. What's happened here is 2 things. A has moved along, and it moved along. If we scroll all the way back right up here, it travelled 0.5 metres, then B hits the floor. And this distance we've worked out here, this 1.5, is the distance it travels once the string becomes slack. So the total distance here is going to be the 1.5, add the original 0.5, which gives you a total of 2 metres. But remember, that is to now, it is actually to 3 significant figures, but I've written them to 2 significant figures there. Right, and that is how to answer question 14, which is the combination of SUVAT. 2 different stages of SUVAT, really, when you think about it, when it's a connected particle and when the the string is slack, so there is no tension. So 2 different stages. That's quite common in an A-level question, of those 2 different stages, and it's one that they quite like because the acceleration will change and it gets you to have to do another stage. So do look out for those and do keep thinking when you're doing those.